Hello everyone! In the last lecture, we have discussed the fundamental working principles of the electric motors, electric machines in general, and today we are going to focus more on the three-phase induction motors. We said that the induction motors are a special type of electric motors that gained a lot of popularity in industry and in many real-life applications. Today we are going to discuss the modeling and analysis of the three-phase induction motors. So let's get started. So the focus today in this lecture is to develop the equivalent circuit for the induction motor in a similar way that you have done with the transformers. Basically, we are going to understand the meaning of asynchronous operation and slip, and also we are going to analyze mathematically the equivalent circuit. Then we are going to look at some performance analysis metrics for the induction motors. We are going to understand the meaning of the power flow from the input to the output and the types of losses. We are also going to discuss the torque versus the speed curve and then come up with their equation. And we will also understand the effect of the wound rotor and the external rotor resistance on varying the speed and the torque of the motor. And this will be the end of the lecture. So today we are going to come up with this equivalent circuit for the induction motor. You may recognize that it is quite similar to the equivalent circuit for a transformer. So that will be our starting point, but notice that there is some differences between the transformers and motors. And that is that the secondary circuit, which is the rotor in the case of a motor, is rotating at a different speed compared to the stator's magnetic field. And we are going today to highlight these differences and how they affect the equivalent circuit. But before going into that, it is also important to understand that the parameters of the equivalent circuit of induction machines in general are crucial when considering advanced control techniques. And the equivalent circuit, in fact, of any machine shows the various parameters of the machine, such as its ohmic losses and also other losses and their effect on the performance on the motor. And it is also necessary to gain a better understanding of the properties and behaviors of the induction motors. So notice that the losses are modeled just by an inductor and a resistor. The copper losses are occurred in the windings, so the winding resistance is taken into account. Also, the winding has inductance for which there is a voltage drop due to the inductive reactance, and also a term called the power factor comes into the picture that we will discuss later on.
Let us remember the rotor construction. So if we look at the end view of the rotor, we can see that the outer part is made of copper or aluminum, and inside of it there are the steel laminations, and the rotor is connected to a shaft where you can connect the load over here. Remember that it looks something like a cage, and it might have a number of magnetic pole pairs. Well, these magnetic poles, they are related, they are part of the stator, and the inside over here, the gray part, is the rotor. So we have seen before that the induction motors, they operate on the principle of induced currents. And these, there are still two magnetic fields. One is from the rotor and the other one is from the stator. But the rotor's field is induced by the stator field. So effectively, we can think of the induction motor as a rotating transformer. The stator is like the primary of a transformer and creates the initial field, inducing voltages and currents in the secondary rotor windings. So if we look at the change of the flux of a three-phase induction motor, we can see that it alternates its direction between north to south, and we can consider the sinusoidal flux, we can consider the flux to have a sinusoidal voltage across the rotor bars. And according to Faraday's law, the voltage is equal to the change of the flux over time. And this will cause the sinusoidal currents to flow along the rotor bars, given that they are short-circuited by the end rings. Okay, now let's make things a little bit more interesting. So remember from the last lecture on the three-phase induction motors, a rotating magnetic field is created in the stator with the same frequency as the source. And with the rotor locked, the rotating field cuts across the rotor bars and induces a voltage in all of them. Because the rotor bars are short-circuited by the end rings, the induced voltage causes a large current to flow. The current-carrying conductors are in the path of the flux created by the stator. Consequently, they all experience a strong mechanical force. And as soon as the rotor is released, it rapidly accelerates in the direction of the rotating field. As it picks up the speed, the relative velocity of the field with respect to the rotor diminishes progressively. And this causes both the magnitude and the frequency of the induced voltage to decrease because the rotor bars recut at a slower rate. As the rotor is speeding up, it will never catch up with the revolving field. It is because if the rotor did turn at the same speed as the field, the flux would no longer cut the rotor bars and the induced voltage and current would fall to zero. Under these conditions, the force acting on the rotor bars would also become zero, and the friction and windage would immediately cause the rotor to slow down. In order to identify the direction of the motion of the rotor, we are going to use the Fleming's left-hand rule, which states that the forefinger is pointed towards the field, the magnetic field from north to south, and if the second finger points towards the current from positive to negative, then the thumb is going to point towards the movement of the rotor. In fact, Faraday showed that passing a current through a conductor freely suspended in a fixed magnetic field creates a force which causes the conductor to move through the field. More generally, the force created by the current, known also as the Lorentz force, acts between the current conductor and the magnetic field, or the magnetic creating the field. So we can say that the magnitude of the force acting on the conductor is given by the product of the stator flux density, the rotor current, and the length of the rotor bar. So notice that all these three parameters affect the magnitude of the force. Now it is time to discuss the relationship between the torque of the motor and the speed of the rotation. Remember that the torque in Newton meter is equal to the product of the force and the distance, which is identified by the air gap distance over here. So generally speaking, the torque produced by a motor is proportional to the current. Remember that the force is related to the current, which means that the torque is also related proportionally to the current it consumes, and also proportional to the flux and the air gap. The starting torque, when the speed is zero, may be about 70 to 90% of its maximum, rising to a peak as the speed increases, then falling sharply. We will see that in a minute. So the torque developed by a motor depends upon its speed. The relationship cannot be expressed by a simple equation. Instead, what we will do is we will look at the torque speed curve and we will use that to understand the relationship. So the first thing is that we will get to understand what is the torque when the motor is rotating at synchronous speed. So at synchronous speed, which is identified as ns, if the rotor was rotating at this speed, then the rotor would be traveling at the same speed as the stator magnetic field. This is the meaning of synchronous speed. And therefore, the flux at any point on the rotor would be constant similar to a DC, so it is just a constant value. And remember, if there is no change in the flux in terms of time, so if that parameter is 0, then the induced voltage is also 0, which means that the torque is also 0. So this difference in speed between the rotor mechanic speed and the rotor magnetic field speed is important and needed in order to produce the torque. Okay, so now that we understood that at speed 0, the torque would be somewhere over here, and when the speed is at synchronous speed, the torque is 0. Now let's see what happens in between. To understand this, it is important to know that when a motor starts to rotate from rest, a locked rotor torque or breakaway torque is developed. It is usually larger than the full load torque. And then as the motor starts up, a pull-up torque is developed as the motor speeds up. The torque continues to increase until it reaches to the breakdown torque. And in this case, the motor runs faster and faster. This is the peak torque that can be developed by the motor. As the motor goes through the breakdown torque and its speeds continues to increase, the torque drops, and as the rotor speed approaches the synchronous speed, the torque becomes 0. Now imagine that a mechanical load is applied to the shaft of the rotor. The motor will begin to slow down, and the revolving field will cut the rotor bars at a higher and higher rate. The induced voltage and the resulting currents in the bars will increase progressively, producing a greater and greater motor torque. The motor speed will increase to drop, or it will cease to drop actually, when the motor torque is exactly equal to the load torque. The motor and the mechanical load now reach a state of equilibrium, and the motor will turn at a constant speed. If the mechanical load increases, the speed will drop until the motor torque is again equal to the load torque. And as soon as the two torques are in balance, the motor will run at a constant but at a lower speed. So now we will notice that we are talking about different torques. So there is the motor torque, the load torque, and something that is called the acceleration torque. As opposed to the load torque, which is constant, the acceleration torque is the required torque to accelerate or decelerate an inertial load up to its target speed. It is only present when accelerating or decelerating an inertial load. So this is the acceleration load, and it is given by the product of the moment of inertia of the load and the acceleration. Note that later on we will derive an equation for this curve using the equivalent circuit model. Also, note that the motor torque is the sum of the load torque and the acceleration torque. Now notice that the curve in red is for a motor driving a load, which has a load torque curve shown in black. Now the motor is working at this operation point. So over here is the operation point at a specific speed. Any disturbance to the motor system causes a reduction in the speed. And at lower speeds, the motor torque is greater than the load torque. Consequently, the motor will accelerate and the operation will be restored to the operation point. A similar result happens if there was an increase in speed caused by the disturbance. That's because the rotor magnet speed is still identical to the stator magnetic speed. So it is necessary to keep the synchronization between the stator magnet and the rotor magnet for producing a stable net torque. Also, note that the induction motor always runs at a lower speed, denoted by Nr, than the synchronous speed. And that's why we call it an asynchronous motor. The difference between the synchronous speed and the rotor speed expressed as as a percent of the synchronous speed over here, it is called the slip, and we denote it as S. Notice that if we know the slip, we will be able to understand what is the voltage frequency compared to the source frequency. So when the speed of the rotor is 0, the slip is equal to 1. And in this case, the voltage, the rotor voltage frequency is at the maximum. And as the speed increases, that frequency decreases until reaching to 0. A similar case happens to the rotor voltage magnitude. It is equal to S times the maximum voltage of the rotor. Okay, so now as we have an understanding on the relationship between the torque of the motor and the speed of the rotor, it is time to develop or come up with the equivalent circuit of the motor.